Welcome back, and in this module we will look at logic programming. So this module we have two sets of lectures. In the first set we will first introduce a subset of propositional logic that we will use, and having a subset of a language is often useful. Typically you want to do something more tractable for a specific use case. We use the idea of a simple subset of propositional logic mainly as a teaching tool to help get some major points across without having to get bogged down in a lot of additional technical details. We then talk about world-based semantics, and we introduce the ideas of logical rules that we build into programs, and we look at the ideas of a minimal model and a fixed point operator as an efficient means to compute the answer to entailment queries. Then we build on top of all that to support open world reasoning. And most of what we've looked at to date has been this closed world assumption, which means that if something is not true, it's deemed to be false. With open world, if something is not true, we say that it's uncertain. And it could become either true or false depending on the evidence. So extending a framework like even propositional logic to allow for this causes us to look at a bunch of additional concerns, and one of the most important ones is the way we finish off the module is by looking at inconsistency in the knowledge base. So welcome to the module on logic programs. I hope you enjoy what's up next. Welcome back. In this class we will introduce a simple logic, and this is a subset of a propositional logic that we will use for purposes of learning in this and subsequent lectures. And so first we will explain why this is a good idea to do, and then we will move on to formulating semantic and satisfaction relationships, particularly focused on logical rules, which are different from things like proof rules and implications that we learned about earlier. So the logic that we will introduce today is a propositional logic. We've had previous lectures where we went through a more complete propositional logic in great detail. Here we will only use some of those components. And it makes sense to do this from time to time because sometimes you don't need all that power. The first piece of formalism we will have is we'll assume there is a set of ground atoms, set A. And then we will also define what's called a world semantic. So in earlier lectures we looked at propositional formulas and we looked at truth assignments of truth values to propositional variables. Here we will look at the same idea but a little bit differently, where a world is just a subset of the ground atoms that are true. So you could think of converting a world to a truth table by taking all the atoms in the world, setting those to true in the truth table, and setting everything else to be false, and it's the same thing. And so we say a world satisfies an atom if the atom is an element of the world, or formally we have right here. Now we'll also have two special symbols, true and false. True is called a tautology. It's a ground atom that's always true. And false is called a contradiction. It's always false. And all worlds will satisfy true, and none of the worlds will satisfy false. Now, again, why would you want to make a subset of a logic? Well, you may have certain applications where you don't need the full power. You can then make mathematical guarantees about taking that subset of the logic that might be good enough for your specific application. In this lecture and subsequent lectures, we're going to use what we call a simple logic here as just a learning tool. So this way we can teach you about some key concepts and again not get too bogged down in a lot of additional mathematical details. We can kind of deal with that later on. Okay, so our first logical operator in the simple logic will be conjunction. And this is going to be defined very simply where if F is an atom or a conjunction and A is another atom, then F and A is a conjunction. And we say that the world satisfies F and A if the world satisfies both of them. And this allows, this allows for some nice recursion because we can just plug another conjunction into F and keep tacking additional atoms on as we want, just like we normally do. Now note, unlike in the full propositional logic, we are not defining F and A as arbitrary logical formulas. F is always a conjunction and A is always an atom. In this logic, at least for now, we will not have negation. The other logical operator we'll have is a rule. Now, this looks like an implication arrow, but it's going the other way. And that's because this is not an implication, it is a little bit different. And we say if F is a conjunction, and this is the body of the rule, and A is an atom called the head. So we say if F, then A. Now, if F is equal to a tautology, we just put the arrow followed by the head of the rule. And for satisfaction, this is kind of where things get a little bit nuanced, so pay close attention. We say a world satisfies F then A if the world satisfies A or the world does not satisfy F. Now, this is different than an implication because a world not satisfying F is not necessarily the same as the world satisfying the negation of F. And so with the implication, we have A then B, so you can think of F then A in our case, which would be logically equivalent to not A or B. Here, we are not making the same statement because one, there is no negation, and there's no disjunction either. There's no or in this language. But more importantly is item 2, and that the idea of a world not satisfying a conjunction is not necessarily equivalent to the world satisfying a negation of a conjunction. Later on in a few lectures, we will get into open world reasoning, and this becomes more important. Okay, so let's do some quick examples. So we have 2 rules, rained, then grass is wet, and then we have water running and the sprinkler on, then the grass is wet. And we have 2 worlds. World 1 says the grass is wet and it rained, and world 2 says sprinkler on and raining. So does world 1 satisfy rule 1? And the answer is yes. Both the head and the body are true, so it has to. Does world 1 satisfy rule 2? Well, the head is true, so it must satisfy it. Does world 2 satisfy rule 1? And the answer again is yes. And finally, does world 2 satisfy rule 2? Now here the answer is no, because only the rule body is satisfied, but not the head. So that wraps it up for our introduction to our simple logic. Please stay tuned for more content. Welcome back. In this lecture, we will explore logic programs. Here are our objectives. Okay, so earlier on, we introduced a simple logic, and if you need a little refresher, here you go. The simple logic basically is a propositional logic, and it only has 2 operators. It has conjunction and a rule. And the conjunction is just an and of a bunch of atoms, and a rule has a conjunction in the body and a single atom in the head. And we also have this thing called a fact where the body of the rule is just true. Okay, so a logic program, really easy to define. It's just a simple set of those rules. And we often use the symbol capital Pi to denote a logic program, and you'll see things like pi facts and pi rules to denote the set of facts and rules that make up the program. Okay, so how is a logic program satisfied? Well, we say a world satisfies that logic program if for all the rules and facts for that matter in the logic program, the world satisfies each of them. So that's pretty straightforward. And if a world satisfies a program, we say it is a model of that program. So here's a quick example. So we have a logic program pi. It has 2 rules and 2 facts. The first rule says if it rained, then the grass is wet. The second one says if the sprinkler is on and the water is running, then the grass is wet. And we have 2 facts, the sprinkler is on and that it rained. And okay, so we have a couple of worlds. We have the world being that the grass is wet, it rained, and the sprinkler is on. So that world satisfies everything because it has to satisfy the sprinkler being on and it rained because those are facts. And it also has to satisfy grass is wet because of rule R1. Okay. World 2 says the grass is wet, it rained, the sprinkler is on, and the water is running. And so this one also is a model of the logic program. It has this one extra atom, water is running. That doesn't necessarily have to be true, but there's nothing in the logic program that says it shouldn't be, so why not? So next you have worlds 3 and 4. Neither of these happen to satisfy the program. World 3 doesn't satisfy it because it doesn't have rained, and rained is a fact. And world 4 doesn't satisfy it because the grass is not wet in world 4, and it clearly has to be because of rule 1. This is if it rained, then the grass has to be wet. So there you go. So you may have noticed in that example that we had the world that had that extra atom, and there was nothing in the logic program saying that the atom should be there, but nothing saying it shouldn't either. And you could imagine that if you had a whole bunch of extra atoms, you could have just a whole bunch of worlds that have all this information that was not necessarily specified by the program. So we're going to introduce some concepts to help us understand how to differentiate between the worlds. So the first is a full ordering. So this is a mathematical concept. We're introducing it for sake of completion. A full ordering is just you have a set of elements and there is a full order between them. So any pair of elements, they can be ordered. So the easiest thing to think about is you have the set of natural numbers and you have the relationship less than or equal to. Every natural number is related to every other natural number by less than or equal to. So you have 2 natural numbers, A and B. It's either A is less than or equal to B or B is less than or equal to A. And that's it. They have to be comparable. Now partial ordering is a little different. A lot of the elements you can compare, but some are not comparable. So a great example of this is looking at the set of all subsets of a set of elements, or the power set. We could compare these with the subset relationship. So let's say we have a universe of elements A, B, and C, and we can look at subsets B and C, and these are comparable because C is a subset of BC. However, if we have subsets BC and AC, they're not comparable because one is not the subset of the other. So this is a partial ordering. All of these subsets of A, B, C, some of them we can compare with the subset relationship, others we cannot. So we can use this idea over worlds. Remember, worlds is our semantic structure, and we can say that world 1 is below world 2 if and only if world 1 is a subset of world 2. And when we talk about ordering the semantic structure, we will often use this like square subset symbol. And the reason being is that, and we'll see this in a little bit later lecture, that you will not always have worlds which are a direct set representation. Maybe we have, maybe we have like a probability distribution, or maybe we have, we have introduced something later on called the interpretation that is a mapping to different kinds of values. So you will see this square subset symbol often used. And we will use the term below to say that one world is below another. So this idea of a minimal model. So we could say that if we have a bunch of worlds, a world is a minimal model of a program if there is no other world that is below it. And so we could think of this as kind of the smallest number of things needed to be true in order to satisfy the program. Now, why is this important? Well, you may remember in an earlier lecture on propositional logic, we talked about an idea of entailment. Well, actually, hold on a second. First, let's do a quick example, and then we'll circle back to why this is important. So anyway, we have our logic program about the grass being wet and it rained, and we have the same worlds as we did a little while ago. And so clearly, both these worlds, they satisfy the logic program, but world 1 is below world 2 because it's a subset. And so world 2 cannot be a minimal model because it is above world 1. So then the question is world 1 a minimal model? And this becomes our focus in the next lecture, where we go over an approach called the Fixpoint operator that we can use to find the minimal model in our simple logic. Another way to show it is there any element of world 1 that could be removed and it still satisfies the program? So we can't remove any of those elements, so it turns out indeed that world 1 is a minimal model of program pi. Okay, so going back to a little bit before, why is this important? Well, if you recall from the earlier block on propositional logic, we talked about this idea of entailment, and we say that a program pi, a collection of logical sentences pi, entails A if for all worlds that satisfy pi, those worlds also satisfy A. So the only way we could be sure that all the worlds satisfy A is if W is a minimal model, because W as a minimal model would be a subset of everything else. And so if you can find the minimal model, you just have to check, is A in that world, and you're done. You've solved the entailment problem. So it seems much easier than going through and trying to enumerate all the worlds that satisfy your program. And so again, this is just stating that. So if we can find it, we can just check. And then all other models must contain the minimal model. So stay tuned for more content. We will soon go into how to go about and find the minimal model. Welcome back. In this lecture, we will look at the Fixpoint operator. Here are the lesson objectives. Okay, so in propositional logic, we introduced this idea of entailment, and we also talked about a little subset of propositional logic that we're using for teaching purposes. And we're saying in this propositional logic, logic program pi entails atom A if for all worlds that satisfy the program, they also satisfy A. And then we introduce this idea of a minimal model, which we have this subset relationship amongst worlds. And we say a world is a minimal model for pi if it is a model of pi and there's no other world that is below W. So that W prime doesn't exist in that bottom part. And the minimal model is important for entailment because since all other models of pi got to contain the minimal model, if we know the minimal model, we just check if that atom that we care about entailment is in the minimal model, and we're good to go. And so this is really nice because it allows us to identify everything we can conclude from the logic program. So you could think practically, if I have a logic program, I have all these rules, and then in a given environment, the agent's moving through the environment, the sensors found all these facts. What things about those facts can I conclude? Well, I can figure out everything from those facts, at least in the simple logic, just by using the fixed point operator, because it'll give me a minimal model. And that's what we're going to talk about today. So the first piece is this thing called lattice theory from mathematics. And if you have a partial ordering over elements, you can potentially have a lattice structure over that. So if we look at worlds, like in this example, we have atoms A1, A2, and A3. And here we've listed out all the possible worlds that could be formed. We have the empty set, A1 by itself, we have a bunch of sets of 2 elements, and then we have the whole thing, A1, A2, A3. Well, we can relate all these together through the partial ordering, and we see that the empty set, that's below everything. That's called the bottom element. And sometimes you even see this symbol here. Okay, an upside, like kind of like an upside down T. So the empty set is below everything. The singletons are all right above it. Now notice that there's no arrows between the different singletons because they are not comparable. None of them are a subset or a superset of each other. But those in turn are all a subset of every set of 2 elements. And everything in the whole lattice is a subset of the complete set of elements, and this is what's called top. And this has like a T kind of symbol for it. Okay? So anyway, you have this lattice structure. So now we introduce the fixed point operator. And so given a program pi, function t pi is a function that maps worlds to worlds. And formally it's like this. T pi of w equals w unioned with all the rule heads such that the body of the rule is a subset of w. And so intuitively you could think of this is everything that was true plus anything that's true because the body is suddenly true. So those rules fire, we say. So here's some examples. So let's say we have universe of atoms A1, A2, A3. Here are all our subsets again. And let's say we have this logic program pi and it has a fact A1, rule A1 to A2, and rule that should be actually A2 to A3. And so we have, so if you apply the fixed point operator on world A2, then you get A1, A2, and A3. If you apply it on A3, you get A1 and A3. You don't get A2 here because there's nothing that concludes A2 that sits as a fact in the program or fires as a result of A3. If you have the empty set, you only get A1 because it's the only fact. None of the other rules fires. So you may notice in that previous example, let's go back to it for a second, that everything here is only one step of inference. Some of you may see this and say, hey, you know, with that last one, you just got A1, but doesn't A1 lead you to A2? Well, yeah, but A1 wasn't true over here. And so we would need another step. We would need to apply the fixed point operator again. And ideally, we want to do this again and again and again until we can't go any further, because we want to conclude as much stuff as we could. And so that's why we have this idea of multiple applications of the fixed point operator. So I is the number of times we want to apply the fixed point operator, and we say, so t pi I of w equals t pi of w if I equals 1. This is one application of it. And if you're doing more than one application, it's t pi, and then here it's applied to the world on one less application. And now here's kind of the punchline. We say that a fixed point exists if ti plus 1 of w equals to ti plus w. Because once you're here, if you apply t any more times, you're just going to get the same thing over and over again. So you're done. That's a fixed point. So here's an example. So here again is the same atoms we had a minute ago. And here is the same program. And so our first application, let's start with the empty set. We apply the fixed point operator 1. You saw just like before, we get A1. Now, 2 applications of it. Now you get A2. Going with 3, you get A1, A2, and A3. Applying it a 4th time, you don't get anything more. So clearly here, if we keep applying t, we're just going to get A1, 2, and 3 over and over again. So there's no point in going beyond 4. We've converged. We've reached the fixed point. Now, how do we know it's going to get to a fixed point? How do we know that the operator is going to stop? Well, first off, anytime that we apply it, we're going to get some information on the elements of the program that led to the conclusion. And so here, again, going to the example we just ran through, we got to A1. We know that that's the result of the application of the fact. To compute this, you have to know what rule was applied. Likewise here, we know rule A1, then A2 was applied, and finally here, A2 to A3. So what's really neat about this, without going into the mathematical proof behind it, is the fixed point operator, any atom that's the result of a fixed point computation, there is a series of rules that has to have fired in order to get you there. And so the fixed point operator inherently allows for multi-step inference, and this is very powerful. This is going beyond just a simple reactive agent that just perceives something and labels the scene as, aha, there's a window there. This actually allows for a higher level of reasoning by going through things step by step by step. And so it turns out that the fixed point, if it exists, it corresponds with the minimal model. And so we know this because we can prove that anything that's in that the result of the fixed point operator, there has to be that chain of rules to get you there. And so if you remove any of those elements from the output of the fixed point operator, that world no longer satisfies everything, because if it doesn't, that means there's always one more rule that still needs to be applied. So we know that if there is a fixed point, that it must be a minimal model based on this intuition. Now, how do we show that the fixed point actually exists, though? And this is where we use an idea introduced in the 50s, actually, the Tarski-Napster fixed point theorem. And this says that any monotonic function over complete lattice is guaranteed to have a fixed point. And so this can be applied, this is a mathematical theorem, but it can be applied directly to logic. In our case, we know that the set of worlds does form a complete lattice. And the fixed point operator is monotonic because it moves up that lattice structure. It always is just adding things to that set. So one more example before we wrap up. Here's our favorite grass is wet if it rained example. And so again, we start with the empty set. And it turns out the sprinkler is on and it rained because those two facts became true. Then the second application, now we know that the grass is wet. In the third application, we get the same thing, so we know we've converged and reached the fixed point. So thank you for tuning in. Stay tuned for more content. Welcome back. In this lecture, we will introduce the idea of open world reasoning and compare it with the closed world assumption that we've made so far. Here are the lesson objectives. Okay, so if you recall earlier on, we talked about this idea of an agent. The agent has sensors. It perceives things from its environment. It does perception. It then reasons about those things, and it takes action. Now, the environment, we also talked about some aspects of that, and we named a couple different ways to think about the environment, and kind of two that I'm going to highlight in particular are this idea of fully versus partially observable and known versus learned. And especially when you have these properties of the environment, making what we called the closed world assumption, where we assume things not known to be true are automatically false, this could be potentially problematic in these two scenarios. And so a great example of a closed world assumption is chess. Because in chess, since you observe everything and the environment is totally known, if I don't see a piece on a certain square in the board, I know it's not there. So I know that square is not inhabited by that piece because I see it, I have complete information. If that piece is in a new square, I assume the square it used to be on is no longer inhabited by that particular piece. But if we look at autonomous driving, this uses the open world assumption. So if you see a person while driving a car cross the street and there's another vehicle in front of you, that person will disappear for a couple of seconds when he is occluded by that other vehicle. But that person didn't go away. It comes out the other side. There weren't maybe two people, there was one person that was occluded. So we have to make conclusions about that period of time where that individual was occluded. And this is a great example of the open world assumption. Maybe that individual walked in another direction while he or she was occluded and is somewhere totally different. And maybe their location at the time we didn't see them is unknown. And so these differences between open and closed world, they make a really big difference in real world applications. So let's talk about this a little more. Closed world, again, is anything not observed is automatically false. That's your default. With open world, anything not observed is unknown. And so your default is unknown. So, okay, let's go back to the simple logic that we introduced. What do we need to do to support open world reasoning? Well, first we need to modify the semantics, because the idea of a world where everything that's not true is false is inherently suited only for closed world. So we have to do something about that. In this lecture, we're going to focus on the changes to the semantics. Later on, we're going to add negation, because that's going to be useful to conclude that some things are not true. And of course, we have to modify our rules to allow for negation if we're doing this. Okay, so we're going to have this new semantic structure. We used to talk about worlds when we had a closed world assumption. Now we'll talk about interpretations. And to support interpretation is just a mapping of atomic propositions. In our simple case, it'll be just a one of three values: true, false, or unknown. So we're just adding one more potential state of being an atom can be in. And that's it. Now there's other things, if you look at the literature, you'll see that you can associate atoms with real values or intervals or elements of another lattice structure, and that's all really great and important stuff. But for now, just to get our feet wet, we'll just assume it can have one of three values, because adding that one additional value already precludes us from using the simple set notation of worlds. So here's our little example. We have atoms of the grass being wet, the sprinkler being on, and here are just some example interpretations. Interpretation I1 says that everything is unknown. I2, we have the grass is wet, it rained and the sprinkler is on, but the water is not running and the grass is not dry. And then we have, likewise with 3 and 4, various configurations of truth and knowledge. So how do you do satisfaction with interpretations? It's not too difficult. We say an interpretation satisfies an atom if it maps that atom to true. So formally we write I models A if I of A equals true, or we say T here. And of course, just like before, we'll still have true and false, the tautology and the contradiction, and all interpretations will always satisfy true and none of them will satisfy false. So we'll still have a partial ordering. Now here it's going to be a little different than the partial ordering we had with worlds. With worlds, our partial ordering was the same as the subset operation because worlds themselves were sets of elements. So with interpretations, we say I1 is below I2 if and only if for each atom A, if I of A equals true, then I2 of A must be true, and if I1 of A equals false, then I2 of A equals false. So what this is implying is that in I1, you have things that are true, false, or unknown. Everything true and false must still be maintained by the interpretation that is above it. However, everything that's unknown can be further filled in. So you could think of I2 has more stuff filled in as being true or false than I1. There's more knowledge. So let's show some examples. Here's the interpretations we had from a couple of slides ago. And I1 and I2, notice I1 is going to be below every other interpretation for this set of atoms because everything in I1 is unknown. It's going to be below everything. So it's, of course, below I2 that's completely filled in. And we see that I2 is filling in the blanks. If you think of the U's as blanks and true and false as having a value, I2 is filling those in. Likewise, I3 is also below I2. And this is because I2 is everything filled in. I3 has some things filled in. They're filled in the same way as I2 because these are all true and these are all true. But some things are not. I3 is also below I4. I4 is not completely filled in. You still have this one U. But it's more filled in than I3, and it still maintains everything that I3 has. Now let's say, for example, that we have I5, and let's say we have this is true, this is false, this is true, this is unknown, and this is unknown. Okay? So I3 is not comparable to I5. It's not either above or below, and that would be because of this truth value here for if it rained, where I5 is saying it's false. Since those are different, these two cannot be compared. Notice this is a big difference from worlds, because in worlds, if something is false, that's going to be, and everything else is the same, it's going to be below the other world. Here, false is knowledge in the open world assumption, so they're not comparable. So that's our quick introduction to open world. Stay tuned for more content because we're going to explore this a bit further. Welcome back. In this lecture, we will talk about negation and open world logic. And so here are the lesson objectives. Now, for those of you who had like an electrical engineering course or some other course where you had some basic logical principles, you may be wondering, what's the big deal with negation? Well, it turns out that negation often makes things more difficult in logic from a computational standpoint. And if you don't need negation, so like if everything you're doing is closed world and you can safely assume everything is false and only gets more true, you don't care about the negation of what you're reasoning about, then by all means you should probably design your logic-based system without negation. You'll probably be making things a lot easier. But obviously, it's good to have this notion of negation. It really helps reasoning and expressibility. So we do need to study it and consider it, especially in the case of open world reasoning. So if you recall, we talked about this semantic structure called an interpretation, which you can think of as a truth assignment for ground atoms in a propositional logic, except instead of everything just being true and false, we have this other value being uncertain or unknown, and we could think of it as like a blank space, and we can allow it to be filled in with true or false. So rather than enclosed world where everything is false and becoming more true, here you have everything is uncertain, and it either becomes more true or it becomes more false, but something true and false are not directly comparable. And so we had this notion of interpretation satisfying atoms. And so we now want to add in negation. So we're going to take our simple logic we introduced a couple of lessons ago. Remember, the simple logic only had conjunction and it had rules, and now we're going to add in this idea of a negation. So it's really simple to define the syntax. If A is an atom, not A is a negation. Again, because we're keeping things very simple, we're only applying negation to single atoms. And we're saying an interpretation satisfies not A if the interpretation of A equals F for false. Now, this is a key point because this is different than when we first introduced propositional logic, where the notion of something not being true is the same as the model not satisfying it. One other side note is we'll often use the term literal to mean either an atom or the negation of an atom. Now let's go back to that little point I was making about not models, which is this symbol here, versus negation. Okay? So not models, you might see interpretation not modeling A, and you think, oh, that means that A is not true. Well, not necessarily. There's two different ways an interpretation can not model something, and that is if it's false or if it's unknown. And only in the first case can we say that it models the negation. In the second case, we still don't have any information. So we extend the idea of, we have the idea of conjunction from before, and we're actually not going to extend it here. We're just going to keep conjunction being over a set of atoms for simplicity's sake. But just know that it makes sense that, hey, you would want in your conjunction maybe this to be of literals instead of atoms to allow negation. If you recall from earlier, we used the conjunction just to set up the body of a rule. We're taking this kind of step by step, so for now, we're not going to have negation in the rule body, so we're not going to have it in the conjunction. But in the rule, we're going to allow literal to be in the head. And now this means you can now conclude either a positive or a negative aspect of reality. And so remember, again, our definition of satisfaction, we're saying I models if F then H, if I models H, or I does not satisfy F. And again, that's not the same as saying I satisfies not F. So for a logic program, it's the same definition of satisfaction. The interpretation must satisfy all the rules in the program to satisfy the program. And now here we have our logic program, and we have added a new rule because we are now allowed to have negation, so we've added rule 3. And rule 3 says that if the grass is wet, it is not dry. Makes sense. And so we have the following interpretations. And interpretations 2 and 4 satisfy the program. 1 and 3 do not. 1 clearly doesn't because 1 just says everything is unknown. And we know that just by looking at facts 1 and 2. There are some things that are known even before you start applying rules. Interpretation 4 has interpretation 3 does not satisfy it because it does not know if the grass is wet or dry. So remember, uncertain is not the same as falsehood. So interpretation 3 does not satisfy. Interpretation 2 does, because it tells you that it rained. It tells you that the sprinkler is on, which, both these things you have to be because those are facts. And interpretation 4 does that as well. And then as we do to rule 1, we can conclude the grass is wet. So rule 1. And rule 3, we can conclude the grass is not dry. And there is nothing that allows us to conclude that the water is running, because it's not a fact and it doesn't appear in any of the rules that fires. But there's nothing saying that that's not the case. So, we have both interpretation 2 and 4 both satisfied. So that wraps it up for our introduction to negation and satisfaction relationships with open world logic. Stay tuned for more content. Welcome back. In this lecture, we'll talk about inference in open world reasoning. Here are the lesson objectives. Okay, so earlier we had this simple logic. We allowed for the open world assumption, so things could be unknown, true, or false. And we have this notion of a rule that you have a conjunction of atoms in the body, and in the head you have a literal, meaning a rule could be used to conclude something that's either true or false. And then we have a logic program that's just a collection of these rules. And we're going to add one additional requirement. And so we're going to say if you have a rule, if F then not A, then for any other rule, if G then A, the atoms in F and G are disjoint. And this is a strong requirement. It's not the best thing to have in practice. We're going to use this in this lecture to help talk about inference with open world reasoning. Later on, we're going to relax this assumption. But the basic idea is if you don't have a restriction like this, I could have rule if F then not A, and if F then A, and then that will cause a contradiction. You don't want the same thing to allow you to conclude A and not A at the same time. But we'll talk about that more next lecture. Right now, let's focus on how we have to change the fixed point operator to make it work with open world reasoning. So again, we have this idea of an interpretation, and we have this idea of a minimal model, which is the lowest interpretation in the lattice that satisfies the program. And so here are the adjustments to the fixed point operator. So remember before, fixed point operators map worlds to worlds. Now, fixed point operator maps interpretations to interpretations. So you see these two sets of parentheses because since the fixed point operator is returning a function over atomic propositions, we're saying what, for the returned interpretation, what each value for atom A is going to be. And we're going to say that the fixed point operator is going to give atom A true if there is a rule in the program where the head of the rule equals A, and the body is satisfied by the input interpretation. And likewise, we're going to say it returns false if the head equals not A, and the body is satisfied by the interpretation. And if neither of those things hold, well, we're just going to keep whatever A was on the input. And again, we can define multiple applications of the fixed point operator here, and this allows us to do multi-step inference. And so with that really strong assumption I had early on, we can still be assured that the fixed point operator we'll return a minimal model and the fixed point still exists. And so let's go through a quick example. So we have here our favorite logic program about the grass being wet. And if we start with the lowest interpretation, everything is mapped to uncertain. Then we apply again and we get it rained and the sprinkler is on. They're both true. The next application, now we find out that the grass is wet. One more application, then the grass is not dry. And finally, we've reached convergence, and it's going to stay that way. Now, of course, if we didn't have that assumption, it could be the case where things alternate between true and false. But because we made this assumption, it will still converge. And that's kind of the main thing that we want to have. So that concludes our lecture on inference with open world reasoning. Stay tuned for more content. Welcome back. In this lecture, we will look at logical consistency. And here are the objectives. Okay, so we say a logic program is consistent if there exists an interpretation that satisfies that program. Now here's a quick example of an inconsistent program. Because if we know that it rained and we have two rules, one concluding that if it rained the grass is wet, the other rule concluding that the grass is not wet if it rained, both those things can't be true at the same time. So we say that's inconsistent. There's no interpretation that allows everything here to be satisfied all at once. So you may recall earlier on we made this assumption in our class on open world reasoning where we said that if we have a rule, if F then not A, then for any rule, if G then A, F and G are disjoint. And we said we'd relax this, and as you can see here, this clearly violates this extra assumption. And there's going to probably be cases where this may happen. You can also think of, hey, if I'm learning the rules from some really noisy data, maybe these kind of things will arise. So, we had this really nice fixed point operator we introduced that allowed us to find minimal model when we had this assumption. But now, I'll give you a little hint, it's not going to work when we relax that assumption, at least as, when we totally remove it and allow anything. And let me show you why. So we have this program where that assumption goes away. And we start out, everything's uncertain. So far, so good. And it rained. And the grass, we don't know if it's wet or dry. And now we assume that the grass is wet. But then that same interpretation can allow us to include that the grass is not wet. And then it's wet, and it's not wet. And this can just go on and on and on. What will happen is it'll keep alternating, and it will not reach a fixed point. Now, if you remember, the Tarski-Napster fixed point theorem said that the fixed point operator must be monotonic, where it's got to consistently go up the lattice. If it can't go up and it gets stuck in something like this, it's kind of moving around, we have lost that monotonicity, so we can't say if the fixed point even exists. And this indeed is not a fixed point. It's alternating between a few different interpretations. And actually in a very complicated logic program, you could even see this alternating between like a whole bunch of interpretations. And that's what's called an attractor. And so it's not a fixed point. And so what can we do in cases like this? We have, maybe we can't go through all the rules and make sure some assumption is there. Maybe we're deriving rules from noisy data or talking to experts in a given field who have some rules of thumb that violate it for reasons that aren't directly expressed. And so a couple things that could be done. So first is, hey, if you're creating rules that are coming from a domain expert and you're making restrictions, communicate that. and enforce those restrictions, saying, hey, as soon as you have something that concludes that, this turns off the ability to allow these other rules. If the rules are learned from data, then maybe you want to see if you can adopt an algorithm that will only learn rules that are consistent with each other. Likewise, if you're harnessing rules from a database, you should probably, as a first step, make sure that that underlying database is consistent. And like back when standard SQL databases were the norm, this was often a lot easier than in some of the more contemporary big data systems, things like Mongo and stuff like that, that allow for more lax consistency requirements. Finally, a lot of inconsistency can just be a result of noisy data. And so things like using a probabilistic logic or a fuzzy logic that starts associating real values with truth or falsehood, as opposed to what we call a classical logic, which is what we've been studying to date, can also allow you to deal with this. Now, to be clear, fuzzy and probabilistic logic, they also have a notion of inconsistency, but they, when you're having a data-driven application, these will likely come up less often because you have this kind of space over the reals to move about in to handle that noise, where you don't have that with a more rigid classical logic where everything is just, true, false, or uncertain. So that concludes our lecture on inconsistency. Hope you enjoyed it. Please stay tuned for more content.